You want to hear him?
All right. Sorry for this little IC delay. So thanks everyone for joining us today. I hope you all had a great week. Today we have the pleasure to host Gauthier, who is an assistant professor at UDM and here at Mila. And he'll be sharing with us some thoughts on memorization, generalization, and retraining of modern generative models. So before handing the mic over to you, Gauthier, as usual, let me remind you of some house rules. So clarification questions will be allowed to be asked during the talk. For people in person, in order to ask a question, just raise your hand. I'll give you the mic and wait for the mic so that people online can hear you and your question is heard for the recording. And for people online, you just have to write question or I have the question, and when the time is right, I'll let you directly ask it. There'll also be some additional time at the end of the talk for people to ask further question, make some comments, and have a more formal discussion with Gauthier. That's pretty much it for me. So whenever you're ready, Gauthier, floor is yours.
Thank you, Rim. Thank you, everyone, for your patience. Really apologies. I don't know how. Can you hear me well? Yeah, okay, cool. So today I'm going to talk about two main papers that try to ask questions around modern generative models, and more especially about their ability to generalize and memorize it. So before, I think it's important to be on the same ground. So who among this crowd know what generative model is? Who is very comfortable? I hope almost everyone. Cool. Aaron, you raised your hand. Great. Otherwise, cool. So I'm gonna just do a one-slide summary for people who are not fully familiar with it, and I'm gonna set some very rough foundation of what I care about in the context of generative models. So what we have usually is some samples from a given data distribution that look like this, roughly, and that are labeled usually as real samples. And what we want to do is, okay, it's going to work. We want to learn a model setup that approximates this data distribution. And in particular, what we're interested in is a model that is able to generate samples that are not anymore real, but synthetic. And what we want to do is, ask the question of memorization and generalization with respect to these samples. So in some sense, we kind of forget, the model or the p theta. What we have is just a sample induced by these generative models, and this is what we will try to study. Why do we care about these generated samples? Because they can be useful for many things, such as data augmentation, style transfer, generation of content. I guess you're all aware of this. I hope everybody heard about diffusion models, stable diffusion, GPT, for instance. But there are other applications such as simulating complex differential equations and generating new, basically, solution for this differential equation. But yeah, let's get into the motivation. So I have a question for you. I want you to be active and engage in this talk. If you have questions at any time, please let me know. So I have three models. I'm showing you the samples from these models, and you will be the evaluator today, at least for this 30 seconds. And yeah, basically the question I have for you is like, which model is the best? And of course there is tricks. It seems obvious, but actually, if you go for the obvious answer, you will be wrong. But yeah. So who thinks is the model on the left? Best, I mean, that's complicated. So, for a potential application in terms of downstream task. So if you want to use these samples for data augmentations, for instance. CIFAR 10. So yeah, who thinks it's the left? The middle one? And the right one? I mean, this is CIFAR 10, so everything looks a bit weird. I agree, but okay, I can help you a bit. I can give you what is called the FID score, which is basically lower is better. It's a notion of distance. It's the standard metric that everybody uses, and the point I want to make is like the FID is bad, but I can still give you the FID. So it's approximately 0 for the first one, and 1.9 and 1.8 for the second and third one. And the twist here is that the first model was not really, is kind of a thought experiment. It would be the model that has memorized the training set. And so in some sense, it's a very bad model for data augmentation because it brings nothing new. It's like the training set itself. So it will not, help in any ways for data augmentations. While the second and third model are legit generative models that used to be state-of-the-art, a few years ago. And what's really interesting here is that the one that is probably the one that has been successfully used in terms of downstream tasks for data augmentation is the middle one, which has a worse score than the Stallion Excel, and tends to, kind of the takeaway is that the left one is bad, and it seems that the middle one is maybe the best for data augmentation, which is not really indicated correctly by the score. This is why, maybe we need new scores to evaluate these samples, and hence the motivation of this work. So the work I'm going to present, the first work I'm going to present is a joint work with Marco, who is in the room if you have more questions, and Joey, as well as a bunch of DeepMind people. And basically, we try to evaluate and define generalization for generative models. Any question about the thought experiments or anything so far? No? I like it.
So the problem with this first model being bad was that it was just a data set, right? But
Yeah.
if you are really learning a model and you have a big data set, then there's a compression somewhere. So it can't be memorizing your data set. So you still, FID score could be working. What's the criticism to?
I mean, okay, the criticism is the criticism of the score that says this is amazing, while actually this is purely memorizing. So it's more about the metric, because I kind of agree with you that maybe this don't happen in real life, and it doesn't. We measured it, but we would like a score that actually detects if it happens and penalizes.
All right, thank you.
Cool. So why evaluating generalization and overfitting is important? For the motivation I presented, we want to properly reward models that don't only memorize, but generalize and compress, because it's important for the downstream task, because this is how we will use the model. We will the samples are interesting if they are novel and if they are good. And also, memorization can be a problem when there is some privacy consideration. And I will have example after. So if you memorize training data and your model can leak this training data, that could be a big problem. So at the end, in terms of conclusion, what we want is a score to score the samples that correlates with performance in the downstream task, so which will be due to sample novelty, diversity, and quality. And we want kind of a score that is really penalizing when there is some data copy. Why? Yes?
So yeah, just why the second one? Why isn't the first points enough?
I agree. I agree with you. There are almost two orthogonal directions, almost, in the sense that one is about generalization, while the other one is really about data copying. And at the end of the day, that's true that you can generalize but still memorize some samples. I would argue you don't want too much copying though, because at the end of the day, if half of your samples are just copied of the train set, you may not want this. If you have 1% of your samples are copies, maybe it's fine, and this is what seems to occur in practice. That's why I put a few, but I agree it's the surrogate a bit subtle. But I would say there is some very specific application where you don't want any copying. For instance, for privacy reasons, like your data set, you may have a picture of yourself used in like stable diffusion. And if stable diffusion is able to basically output yourself to your face while you would not like it to happen, that could be an issue. And so yeah, there are two papers that, there are more, but at the time there was two papers investigating this problem, trying to retrieve training examples from stable diffusion models. And long story short, because I lost 10 minutes at the beginning of the talk, so I'm going to be short on this. Long story short, yeah, you can retrieve some training example from the generator itself. So top row are the generated pictures, and bottom row, yeah, you need to look, closely, put your glasses. But these are the training examples that are the closest from the generated one. And I can tell you, if it's too far for you, that they are very, very similar. And I ask some concerns. This one is even more like striking, in my opinion, where the left one is the picture of a real person, and on the right, this is the generated image, which is literally the same. So that's the first motivation. The second one is that generative models have been successfully used for data augmentation in two contexts. The first one is for ImageNet classification. So what you see here, actually, I'm using my cursor since the beginning, but on my slides. So I should use it on yours. So what you see here is basically the performance of different models, different architectures on the ImageNet dataset without, in blue, and with data augmentation using a diffusion model on ImageNet. And what you can see is really a consistent improvement in terms of once you use this data augmentation. So it seems that generative model starts to be useful as a way to do data augmentation, and hence we need a measure of performance that can predict this usefulness. The other setting is adversarial training. So if you're familiar with adversarial examples, these are very small perturbation of the training images, such as you take this one, you compute this perturbation that depends on the model, you get this new image that is for human undistinguishable, but for the model, it becomes an airliner. So famously, Alexander Madry said that AI is a wonderful technology. It's the only technology that can make pig fly. And this is how it makes pig fly. So data augmentation has been used to do adversarial training, meaning basically training the model to properly classify the perturbed examples. And the models that tends to be robust against this perturbation got significantly more robust if they have been trained with data augmentation. So yeah, I hope it's clear motivation for you. Any question? Basically, long story short, generative models starts to be useful. We want to evaluate them properly. How? What do we want for the score? We want several things. We want the score to be interpretable. We want it to give a meaningful value that we are comfortable with. Should be the desiderata of any score. Easy to compute and scalable, of course, in high dimension. These two are pretty obvious. But then, which is a bit more subtle, is the following trichotomy, where we want the score to be comprehensive, meaning sensitive to the sample fidelity, how good looking the single image are, but also diversity, what is the, are all the class represented in the generation, and finally, the one that has maybe been underrated so far, the sample novelty, meaning that we want image that looks good or diverse, but also different from the trainings. And this is what we call novelty, something that's kind of generalized. And in terms of previous work, most of the previous scores, such as inception score, if you are familiar with evaluation, or Fresh inception distance, focus on fidelity and or diversity, but really fail at evaluating the novelty. And this is the first example, the second slide I showed is exactly this illustration that you have very good looking samples, but are not new. They are from the train set, and the score is really giving an excellent score. And what I want to argue today is that you need all these three to kind of measure generalization. Okay, how are we going to do this? We're going to get back to the roots, statistical learning 101. When you start to learn statistics, people are telling you, you should use maximum likelihood to evaluate your generative models. And then you take a deep learning class and nobody does this. So, if we were to use log likelihood to evaluate our models, what we would do is we would train our model. Then we would have this density, and we would evaluate this likelihood on the real data. And the higher this likelihood is, the better the model is. So why are people not doing it? Yeah, so there are several things. Of course, p theta is hard to estimate. There is a lot of generative models where we don't have it. As I said, I want an evaluation metric that uses samples. Samples are not good. I mean, it's not trivial to estimate p theta from the samples. So yeah, curves of dimensionality, distance in pixel space are not that meaningful. Most generative models don't provide density. So what we're gonna do is we're gonna try to estimate the density from sample. That's kind of the idea, and to do it purely from the samples in order to have a model agnostic metric. Also, one of the challenge is we want memorized samples, meaning the ones that are close to the train set, to worsen the density estimation, to make it more peaky. Because if you start to generate training example, it means that you have a kind of peak in terms of density at this point. Yeah, the for one I can go. So how we're gonna do this? We're gonna do this via what we call perceptual likelihood using a mixture of versions. So from this, you can guess what I'm gonna do, but of course I'm gonna detail it. So the step 0 is we need to use 3 sets. The first one is the generated set, the set of generated sample, the one that we will evaluate. We need the train set, and we need a test set. Very interestingly, in generative modeling, people have not have test sets. You look at the most recent data set, there is no test set. I don't know how you can evaluate generalization without a test set. So I want to get back to a test set. It's very important. So what you need is, and what's important is the train set is the one that has been used to train the generative model, hence to generate the samples. And we want a set that has not been used to train the generative model. The first step is the same as what people do for FID and inception score, and in general for computing this performance metric. We're gonna map the sample into a more perceptually meaningful feature space. So what we're gonna do is we're just gonna take our samples and use some deep features. So people in the past use Inception v3, more recently Clip. There are some new evidence that the Dino v2 is better than all this at doing what we want. So we're gonna use Dino v2, but it would work sensibly well with any features. And now we're gonna denote this a phi of a example. Okay, very simple. You all have done this in deep learning class. Then you take the generated samples, and this is where it starts to be slightly tricky. We're gonna estimate the density of the generative models with a mixture of Gaussian. So this density is basically an average of a Gaussian density, where the Gaussians are centered at the generated point. Okay, And what's very important here is that the variance for this Gaussian is set to 1 at the beginning, but will be learned. And this is very important. We will learn the variance of each individual Gaussian. So you have a pretty 2D picture here for you. So the generated points are in orange. You have these 5 points. The density is just a mixture of the Gaussian density with variance 0.1 so far. And you have the training. And we're going to use the train set to learn the bandwidth or the variance of these Gaussians. Does it make sense? Yes. I'm going to take the both questions.
So there are as many Gaussians as the dimensionality of the embedding, or?
No, I mean, the dimensionality of the Gaussian is the dimensionality of the embeddings. Oh, yeah, so yeah,
That was
it's a
the question.
multivariate Gaussian dimension of the dimension of the embedding. So it's, we use a isotropic covariance for just scalability. But we could use like a very complex covariance. Yeah. So yeah, the L2 norm here is basically the distance in the feature space.
So why are you putting it on generated samples rather than the training samples? What's the benefit?
Yeah, so that's a very good question. It's kind of both choices are to a certain extent valid. It's more about precision versus recall to a certain extent. Either you wanna like look at what is the distribution achieved by the generative models, or if you put it on the training samples, it's more like how much of the data distribution the generative model can get. But I feel it's more natural to center it at the generative model.
But both of them are estimating the log likelihood?
I mean, I haven't estimated the log likelihood yet,
Okay.
but
All right.
I mean, like at this point, we want to estimate the density of the generative model in feature space. Yeah. But like long story short, both are valid, and they are. One is more about precision, what you can achieve with your generative model, and the other one is more about recall, which means that it's either how much of the train set is What happened? Hello, I apologize. I don't know what happened. Okay, back. Cool. So, perfect. So I believe, I hope you are convinced that it's quite interpretable. You know, we have something. I mean, that was the easiest, I think, tick mark to check. But yeah, it's between 0 and 100. Lower is better. 0 is the best. It's quite nice. Then the question we wanted to ask is it easy to compute and scalable? It's actually better than the FID. So what we have here is the score for different generative models. And what we plot in particular is the variance of the score over different sampling of the generated distribution. And so what we can see is that it's pretty accurate and it converges to a given value. So it's good, you know, 5,000 samples seems to be enough and estimate the uncertainty. And it's significantly better than the FID, for instance, which is biased. So if you didn't know, the FID is biased, meaning that the more sample you get, the lower the score you have. So
Sorry, what's the test set size for FID here?
because, okay, so you usually for FID, you look at the distance between the generated distribution and a distribution.
Training set.
So now in practice, people do train plus test to have as many samples as possible, because then, you know, you lower your score. At least on CFAR, because CFAR is small. But yeah, I believe it's actually better to look at the distance between generated and test anyways, for, you know, kind of generalization reason, even though I don't think it evaluates very well generalization. But this is what I mean by test set size. So one subtle thing, if you're surprised by the super high value of the FID, because you know by heart the FID score on CFAR, these are high because we use the DynoV2 features that are better at discriminating examples, and so it changes the range of the FID. But the ordering, which is what matters, is the same as with FID most of the time, with inception features. So that's great. We don't need that many samples. It scales well with respect to samples. It's also scaled well in terms of computational time. Solving the log likelihood maximization problem is not too hard. So what we have is a number of samples we use for the score as the x-axis, the time it takes to compute the score. And what we can see is like everything scales linearly. We are happy. It's slightly more expensive than FID, which is in orange. But yeah, linear scaling, we are happy. We cannot do better than this anyways. I mean, we can do sometimes. Linear in the number of generated and training example we use. It doesn't go with the product because they are never. Oh yes. Yeah, so it should go with the product, but it doesn't. Very good point. It doesn't because the main bottleneck is the step one. It's finding the phi of x. Computing the deep embeddings is the most expensive things, and then you are kind of in reasonably big dimension, and this is very well parallelized to compute this the big matrix with all the pairwise distance. And so at the end of the day, what's really the most expensive is just to go over all the examples to compute the features. But yeah, very good point.
It's still technically super low.
Technically, it is, but maybe if you go to 1 million, or maybe at some point it may pick up, but here we went up to 100 examples and it's still linear. But yeah, I agree. At some point it may becomes like quadratic. Cool. So last one, last three one. We wanted to be sensitive to fidelity, diversity, and novelty. The most novel contribution being the one sensitive to novelty. So for fidelity, what we did is we used different transformation. So we took the sample of a SOTA state-of-the-art model, and we replace them with transformed copies. So we decrease the fidelity, maintaining the novelty and the diversity, because we just modify individually each images. And so what we have here is some imperceptible transformation. So if you don't see the difference, it's normal. Basically, it's like compression that are not perceptible for the humans, but that changes actually the pixels slightly. And what we see is the score is relatively not sensitive to this transformation. It's great, while the FID is way much more sensitive. If we take perceptible transformation, so really big decrease in terms of quality now, you see that the score is more sensitive. So here is the score when we do nothing, and the score gets worse as we consider worse transformations, similarly as FID. So first one checked. Question about this one? I think it's okay. For diversity, I will go very quickly, but yeah, it works. It really estimates well diversity. The more classes we have, the lower the score. And so here, we increase the number of classes represented, we have a better score. And on the right one, we look at the diversity intra-class, and the worse it is, the worse the score gets. So long story short, it's measure what we wanted. I think the interesting one that is novel is the one about sample novelty. So what we do here to simulate a lack of novelty is that we start to inject copies of the training set in the generated samples. So we take the state-of-the-art model, and now we are like, what if this state-of-the-art model also has memorized data? And so we do this by replacing generated samples by training set examples, which are simulating pure memorization. And so what we can see for the score is that for low memorization, as you were mentioning, Aaron, it's not that bad. The score is not that unhappy. But if at some point you start to have heavily, like memorize and like basically only generate training set examples instead of novel examples, the quality of the score like really detects it. On the other hand, for FID, the FID is like, yes, go ahead, memorize samples. They look better than the previous ones. And the FID is not able to detect that there is more and more copies of the train set in the generated samples. Yes, Siamak. Yeah.
So I'm wondering, like, if you do kernel density estimation, you're putting these kernels on the training data, right? And would this be a problem there, or they're going to be equivalent anyways?
So we are doing kernel density estimation to a certain extent with some slight subtleties. So the difference is that in kernel density estimation, usually the bandwidth of the kernel is the same for all the kernels.
You could still do that. The main difference that I'm seeing is that you're putting the kernels on the generated samples. So in kernel density estimation, you would put it on the train. You would adjust the variance from the test, from your own tests, validation set separately, and then you evaluate it on the generated samples, basically.
Okay.
In your case, you're putting it on the generated samples. You're setting the bandwidth with the training set, and then evaluating it on tests. So all these data sets are switched, and I'm wondering if that approach, like the traditional way of doing things, will have these problems, or this is.
I see.
The problem with the traditional approach is that this is, for example, the diversity. So you could imagine like a generative model that just produces one high quality sample, and that sample would always have high likelihood of the set density. But it would be not a great generative model diversity.
Okay.
But we do use that in some other points. We could use like a similar approach to evaluate sample quality. By basically, we estimate the density of the training set. You just have to evaluate the likelihood of it.
So there is a difference.
Yeah, there is a difference. I mean, to me, the difference is really like this precision versus recall. Like it's either how well you look at the density of the real data and you look at how well the generated data gets in this density, or the opposite, which is like you look at the density of the generated samples and it's how well the data distribution
But
gets.
geometric, if you think about it, in the end, you're measuring pairwise distances between trained and generated when you calculate the log likelihood, right? So it seems like they should be kind of equal, except for the normalization in your when you.
It's really, I think it's really about like you have two sets, and either you look at, and either you look at like how many red are in the blue, or how many like. So if you see this is train, and this is gen, what you propose is basically looking at who is there. It's the same in that case. No, but yeah, it's who. Okay, I maybe didn't do. It's who is there with respect to the Hall density. So it's like a fraction of red in the blue with respect to the blue normalization, or the fraction of blue in the red with respect to the red normalization. So for instance, the corner case that Marco explained is this one, where your method would do great, but ours would really say it's bad, because a lot of training examples are not represented. And a case where our method would be maybe a bad one is the opposite, of course. So something like this, where we would use this to model the density, and like all the data will be.
So what would be that problem in generative modeling? Like you.
I guess it's like if you have.
Not even be exposed.
Massive diverse samples that have nothing to do.
Yeah, exactly.
So maybe because
you have
our methods are good, you don't have that.
You have like all the great. You generate everything good, but also everything bad. Which seems a bit.
It's very true that our models are more like the small red. Yeah, that's how they made it.
All right, thank you.
Thank you, Siamak, for the great questions. Cool. So, go Alex. Sure. Yeah. I have 10 minutes.
A couple of questions, but so one is, I'm curious. So this is perfect copies, but I guess in practice, what happens more is variants of that. So the generative model will never sample the perfect copy. And the other question is, if I put a bit the reviewer to hat on, so here you said the worst score is 100, and you inject like 100% copied samples, and it doesn't really go to 100. Still stays like 12.
Yeah.
And then also with 20%, it's going down. So it's a huge improvement. I don't want to like trash it. It's a huge improvement with FID, which is like really bad. But isn't it concerning as well?
I agree. So that's the point. So it's a bit within error bar, I would say. But I mean, that's the complex thing, is that you inject copies, but the problem is like these copies are perfect. So, they are perfect diversity and perfect fidelity. So because the score is sensitive to all this, it's still a bit happy, But it's
happening on you're evaluating the test set. So it's because you're evaluating the test set that it makes sense that it would maybe go down. If those samples contribute to more diversity coverage of your model, then it makes sense.
Right, but if it's something that matters, this work should actually be stricter about
okay. So
it wouldn't be hard to do it.
If you're trying to use this as a guarantee against direct copy.
Exactly. So there is two things. Either we want to assess generalization, or we want to assess like memorization. I have a very good answer to do. It's like the next slide, which is that we could look at the generalization gap now, the difference between, the log likelihood on the train and the log likelihood on the test. Because you have fitted on the train and then you evaluate on the test. And this generalization gap really is huge when there are copies, actually. I don't have the slide here, but I can pull it out, I think, for you. It was hidden. No, did I remove it? Oh, it's so sad. It's so sad. I won't do it. But yeah, basically the generalization gap was growing linearly as the number of copies. So you could actually assess that there are copies if there is a generalization gap. So it's very cool. And actually, we will see this in like the current state-of-the-art model. So yeah, the generalization gap, very simple. I think it's nice because it's a very clean definition of, generalization gap, but not for supervised learning, but for generative models. And yeah, the idea is really like the difference between how well this density does on the red points, the trains, and against what she does on the test points. And for instance, we have a nice toy experiments where we have a
Sorry, just on that.
Yeah.
That generalization gap actually, just on this point, the generalization gap would go to infinity, right?
yeah. It
For
goes,
exact copies.
exactly.
So,
I mean, experimentally, you see it exploding, and also with respect to not exact copy, we have experiments where we don't have exact copy but transformed copy. Copies with a small transformation and same behavior. But yeah, it would have been a plot with 10 different lines and unreadable. But yeah, so bias variance trade-off textbooks version. So you have basically as the x-axis how much the model is kind of overfitting the training examples. So I'm gonna dissect this for you. What we did is we created a fake generative models that is basically sampling a training examples and add a small of Gaussian noise. So and basically the bandwidth, the inverse variance of the Gaussian is on the right. So at the beginning you have a lot of noise and you are really noisy around it. I'm gonna go back to here. So here you are very noisy, and as you go to the right, you get less and less noisy and just sample like training points with no noise. And so what we can see is really cool is that both scores, as you start to fit better the data, meaning the noise goes down, the score improves. But with ours, we really reach a sweet spot when the noise is actually representative of the spread of the data, and the score goes up after once we start to overfit. So we really have this nice curve that assess for underfitting and overfitting in terms of generative, at least in this 2D case. On the other hand, you can see that the FID is just always happy. This is great for him. Cool. And we can see similar things for state-of-the-art models on 3 data sets. So what is there? It's like different models ranked by score. So lower is better. On FFHQ, which is a face data set, we want to generate realistic faces. And what's really interesting, to me at least, is that if we plot the generalization gap, so what's the idea here is that if it's the more negative, the more there is a gap between the train likelihood and the test likelihood. And what we seem to see here is that the better the model gets in terms of score, the more they are kind of overfitting. It's not a crazy overfitting, it's basically 5% of their score, but it's still, the amount of overfitting. There is a difference between the likelihood on the train and the likelihood on the test. A bit like for supervised learning, where you fit your train data 100%, but you still have you are not at 100% accuracy on the test. And this is even more true, for instance, on CIFAR, where like the old models are just not overfitting at all. But the more recent state-of-the-art models really have this generalization gap that is growing. So yeah, to wrap up on this, and maybe how much time I have? I can finish at 10:30. Honestly, I can just cut it here. It's okay. 5 minutes? Can I do a paper in 5 minutes? I'm not sure. So yeah, to wrap up, we want the evaluation of generative models can be tricky, and it's not obvious to account for generalization. And we try to propose a score that leverage the knowledge of the training set. It's very important to know what we have used to train the model, and the knowledge of a test set actually that has not been used. to estimate the perceptual density via the samples of the generative model. The score was able to detect memorization. I didn't develop this that much, but we can also use the score with this generalization gap to detect memorization. And it shows the interesting fact that that was expected by the community, but it's a quantitative proof that state-of-the-art generative models are doing benign overfitting in the sense that they slightly are better on the train, they memorize the train, but they also generalize. So yeah, I will not do the other part of the talk. I think it's going to be just a huge rush. So I'm going to just leave it for questions here. Thank you very much. Maybe just a shameless advertisement. The second part of the talk is about the fact that if you generate good samples, you could use them to retrain, to augment your own training, the training of your own generative models. So you have your data, you have a good generative models, you samples, but they are good, let's reuse them to train a new generation of generative models. And you can do this yourself at home, but it also happens on the web. Like a lot of the current big data sets, such as Lion, have generated samples in them because, generated samples are now in the web. The very famous avocado chair generated by DALL-E is, in a lot of websites. If you type avocado chair, this is the first result on Google Image. So these images that are in Lion are purely generated. And so you can ask us if you want after, but we try to define a framework and prove things about the stability of this learning. So you have your generative model, you train it, you generate samples, you put these samples in the train sets, and you retrain, and you regenerate new samples. And the question is like, will it be stable or will you collapse to something that generates garbage? There is no consensus. People think it will collapse. I believe it's a bit more complicated. Ask me questions if you want to.
Keeping the data set.
Yes. So yeah. So the question was whether or not I was keeping the data set in there. That's the kind of the crux of the problem to me. A lot of people were not keeping the data set and showing collapse. But the kind of the catch of the paper is that if you keep the data set and you augment it with generated data, then you maintain the diversity, the original diversity. You don't forget diversity, and so under certain specific condition, you can show stability.
Okay, yeah, that makes sense. I guess my question was kind of related to that and how it's connected to some of the stuff in RL, because it's like a sequential decision where you're generating data, trying to learn from it, and feeding back into yourself. So maybe seems like you've already got a good solution, but maybe we can talk more about it.
I don't know if I have a good solution for sequential decision making, but
just the connections there.
Yeah, I'm very happy to discuss this.
Yeah, but maybe one other part, and maybe I missed it while you were talking, but you've got a model there that should generalize better and not overfit samples. But I'm wondering, is there any cost now in the quality of the samples that are generated from the distribution? Like, do the images still look really crisp versus now that you've got these additional constraints to not memorize the original crisp images?
Yeah, so I mean, it's a score to evaluate. So we are not using the score for the training, but that's true that if we start to evaluate more things, the natural selection process of like what is the state of the art may change.
I think the question might be like, if you use this as your metric to decide what hyperparameters you should use.
Yeah, exactly.
Stop training.
Mm-hmm. Yeah.
Expect to see
you may see slightly less good images, but maybe better for actually what we care about, which is data augmentation or generation of novel content.
Okay.
So we may see less memorization, even though it seems that
that's the point. I'm just wondering, like, where does that trade-off
But it's harder to evaluate. It's very hard to, because when we do human evaluation, usually you show a sample to a human and you're like, is it real or fake? But when you memorize, it's not taken into account. A very good human evaluation would be, here was the train set, get a good sense of what the distribution is.
I don't think that'd be a very good human evaluation. Maybe a few
Yeah.
people in this room could perform that task, but not an
Yeah,
average
yeah.
human.
Because so one big problem with human evaluation is that it's by basically distinguishing between real or fake, which doesn't take into account diversity. I mean, or very tiny bit of diversity. So it's really biased toward fidelity and quality of the images.
Mhm. Great, thank you.
Thank you very much. My question is, when you're refitting the synthetic samples, do you have any criteria, or you think okay, this percent of the samples will be the synthetic data is going back into the model? And the reason I'm asking that is because when memorization happened, like as I remember, I saw the paper, the memorization happens a lot on the minority groups, like on specific parts of this mixture of Gaussian. So I was wondering, can we predict where this memorization happened and then maybe augment only there?
The rest on on the other part of the distribution, you mean, for the augmentation?
I mean, for example, memorization happens when there is an imbalance, when it samples again from things that it didn't have, like a very smooth Gaussian, maybe like a picked one. If
I maybe I have pictures of generalization, so I can memorization. Do I have? Yes. I need to unhide the slide. Let's keep. So for CFAR, this is where memorization happens. Which is, if you don't know, if you're very familiar with CFAR, you will recognize this car because it appears 20 times in the trend set, literally. So it seems that memorization, in that case at least, really happens for repeated examples, like that you really overseas. So I would say the opposite, like majority classes. So your question was about, but like, yeah, and the second part was then how do you reuse the samples to augment the data set? That's a very good question. And I think that's key. It's like, usually when you do data augmentation with these generative models, you are allowed to curate yourself to a certain extent, this data. And so you may want to filter it to make sure that, you don't bring garbage in the data augmentation. And I think that's a key thing that is the difference between doing theory and saying, oh, I'm going to re-augment with everything, and what people really do in practice, which is like trying to make the most of the generated pictures, and in particular, like filtering them, potentially improving them, and so on. And it's a very interesting open question, what are the best, curation and filtration tools? Like a lot of, like the latest state of the art on conditional image generation and stable diffusion is some high-class submissions, where basically one of the big contribution is to curate the Lion dataset to make it having better captions and this kind of stuff. So it seems that it's a huge part right now, like this data science part of machine learning becomes way more important.
We have a question from Beno online.
Beno, I'm all ear.
Okay. I'm gonna read his question. Would you say that image text alignment is in some way also a measure of generalization? If you choose text that was definitely not seen in training, green elephant, inting, yellow blueberry on Mont Royal, it must generalize and can be measured decently by discriminative vision language models? Okay,
that's a super interesting question. So how do we extend these metrics? If I summarize it slightly differently, how do we evaluate text-to-image models? Right now, there is no satisfying evaluation metric. And actually being able to evaluate this, like meaning the quality of the image, but also how related and consistent it is with the query, the text, is a very interesting open question. And I would argue that we're going to try to use these techniques to do it. But yeah, I mean, if you ask, you have a query that is not in the train set, it feels like it should be a good way of measuring generalization, as long as you make sure that the image corresponds to the text. Because right now, how people have been evaluating it is they use the test queries to generate images, and then they have this set of generated images, and they just look at some sort of FID, but without taking into account the fact that the images generated should have something to do with the queries. It's super hard to check that, basically.
Makes sense. Any other question? Yeah.
I just had a question about the stability of data augmentation paper, and I was just wondering, so is one of the assumptions that you have to make about the data augmentation that the ratio of samples that you add, that you augment your data with, is like fixed to some sort of ratio of the original data set? Because I assume you can't just like go on augmenting infinitely.
100%. Your question is the takeaway of the paper, which is that at least for the theory, our result is we should not use a too large fraction of synthetic data for the augmentation. And we have a theoretical bound on how much generated data you can use at each step to augment the train set.
Okay, cool, thanks.
Which is less than 50% right now. I think we can improve it, but right now it's less than 50%.
Thanks. Thanks I love this idea, actually. I think it's really great. Just on the work that you spent most of your time on here, just your evaluation, I guess you showed us results on, so for evidence for overfitting on CFAR.
Yeah.
Do you have evidence for ImageNet? Yeah, you've got the.
Yeah.
So are you seeing it there too?
That's true for ImageNet. So for CFAR, I didn't have the picture.
What is ImageNet 256? That's 256 sized images?
Yeah.
Is that okay?
Yeah. That's a good question. So we had the pictures for CFAR. Did we have some for ImageNet? It's less clear, no? It's less clear. I mean, we don't have the same card 20 times in ImageNet.
I guess I'm kind of wondering if we're at data scales where, like, we might always sort of be at data scales where we're almost kind of at the verge of not really having that kind of overfitting issues. I don't know. I mean, I guess that's a question for you guys. But now we're at least in a position to answer that question.
Yeah, I mean, clearly the overfitting seems benign to some extent. There is a tiny bit. If we look at the numbers here, like there is, the FLS on test is 2 and the FLS on train is 1. So there is still, because I mean, I just did the math.
Yeah.
This one plus that one. So it seems to be a drastic difference. We haven't investigated how much. It's not trivial to find memorized examples on ImageNet. It becomes very subjective. We really want to see them. A lot of people don't want to see them. So I would say it's less obvious as on CFAR. Okay. So I'm not that. If I try to be honest with myself, not that much.
Okay, thanks.
All right, I think we can end officially the talk. Let's take again Gauthier. And I wish you all a great weekend. There won't be any tea talk next week, not to overlap with the G-Flight workshop. Bye.
Yeah, thank you everyone for your questions.
One little myth.